So as we stated in the last section, what we're going to care about in terms of the magnetic flux is how it's changing. Because when you change the magnetic flux through some conducting loop, you can generate an EMF that can drive a current. And all this is encapsulated in Faraday's law and Lenz's law. So Faraday's law of magnetic induction tells us that if you change the magnetic flux through a wire loop, that can cause currents to flow around the loop. So again, you're inducing an EMF that can be used to drive a current around your loop. When you drive a current with an induced EMF, because you've changed the magnetic flux, that current is going to be induced to oppose the change in the magnetic flux. That's going to let us figure out the direction our current is induced around our loop. The easier way to think about that, rather than also tying it up in Faraday's law, is to think about it in terms of Lenz's law. So we'll talk a little more about that in the next section. But fundamentally, what Faraday's law is trying to tell us is that when you change the magnetic flux through a conducting loop, what that does is it induces an EMF within the loop. It's going to create a potential difference around your loop. That potential difference can then drive a current. So when we talk about electromagnetic induction, what we're going to have is we're going to have a current, but in this case it doesn't come from a battery. Right? So there's not a voltage source like a battery sitting in our loop. Instead, we're going to get a current because we're changing the magnetic flux through the loop, which is going to induce an EMF. That induced EMF will act just like a battery and drive a current. If we want to calculate this out, what Faraday's law tells us is that you can calculate the average induced EMF. That's what the lowercase epsilon stands for here, is the average induced EMF. That's going to be equal to, there's a minus sign out front, but we'll talk in a minute about how we're going to sort of get rid of this in a second. N is the number of loops. So you can have a single loop, or you can have multiple loops put together in a coil. And so each one of those individual loops is going to contribute to the magnetic flux, and so therefore will also contribute to the induced EMF. And then we're going to care about how the magnetic flux is changing over time. And we know that the magnetic flux depends on three quantities: the strength of the magnetic field, the area of the loop, and the cosine of the relative angle between the magnetic field and the area vector for our loop. We can calculate out the average induced EMF by thinking about N times what's changing in our BA cosine phi term, dividing by the chunk of time over which we allow it to change. Now, of course, there's that minus sign. What that minus sign is trying to tell us is that the induced EMF is going to oppose the change to the magnetic flux. So fundamentally, whatever the initial magnetic flux is through your loop, that's the value nature would like for it to stay at. So if you increase the magnetic flux, let's say, then you're going to induce an EMF that is going to oppose that increased flux value. Again, the easiest way to think about which direction the current is going to end up going is to use Lenz's law. So what we're going to choose to do with this class is we're basically just going to say, well, let's think about the absolute value of the average induced EMF. And so N, again, that's always positive because that's just a number. Delta T is always positive because time always moves forward. And so we'll need to think about, of these three quantities, we'll just choose to set things up so that we end up with positively valued things, even if these quantities might in fact be decreasing. So that's what the absolute value here is telling us. So we'll be able to use this equation to calculate out the magnitude of the induced EMF, and then we'll use Lenz's law to figure out the direction of the current flow. So working with Faraday's law is really about identifying what's changing in the magnetic flux. And again, there's three parameters that are sitting there. Either your magnetic field is changing because it's increasing or decreasing. the area of your loop is changing, and so maybe that's the area of the loop itself is changing, or it may simply be that the area that is being penetrated by the magnetic field is changing, or the relative orientation between the magnetic field vector and the area vector of your loop are changing. So once we figure out which of those three things are changing, we're going to be well along the way to figuring out how to use Faraday's law to calculate out what the induced EMF is. So let's look at some examples. So for starters, let's say that we're going to change the magnetic field. And so here I've got a conducting loop that's sitting in a magnetic field. My magnetic field in this case happens to point into the page. So to calculate out the magnitude of the induced EMF, I want to think about what the number of loops are, in this case it's just one, times what's changing in the magnetic flux. And of course in this case what's changing is the magnetic field. The value of B is changing. The area of the loop isn't changing. The relative angle between the B and A vectors isn't changing. So I can pull those two things out and I'm left with N times A times the cosine of phi times the absolute value of how the magnetic field is changing over the chunk of time that I allow it to change. So notice, if the field is increasing, that's positive. If the strength of the field is decreasing, delta B is actually negative, but since I want its absolute value, again, I'm not going to worry about the negative, so I end up with just a positively valued induced EMF. Let's look at a couple situations where we allow the area to change. So here's one where what I have is sort of three sides of a circuit, and then I have a bar that goes across this conducting rod that I've bent around in sort of a U shape. And what I can do is I can pull the bar, and so that means that the area inside is increasing. So initially there was this area inside this rectangle. As I pull the bar to the right, the area of my rectangle that closes up the loop has increased. So this is one way that what I can do is say, well, let's change the area. We'll keep the magnetic field the same. We'll keep the orientation the same. So B and cosine phi I can pull out, and I'm left thinking about delta A over delta T. In this case, as I pull the bar to the right, the area is increasing. So delta A would be positive. What if, on the other hand, I took my loop and now its area is fixed, but I'm going to pull it out of the field. So as I pull it out of the field to the right, what I notice is the area being penetrated by the field decreases. So as I pull my loop to the right, less and less area of the loop is being penetrated by the magnetic field. So our picture on the right is showing us a situation where our delta A would be decreasing. It would be negative. But again, since I want the absolute value, I don't have to worry about the minus sign. So we're always going to end up calculating an induced EMF value that's positive. So we've seen how B can change. We've seen how A can change. Well, the last option we've got is what's going on with that relative orientation between B and the normal vector. So if I take my loop, put it in a magnetic field, and then spin it. So I'm going to let my loop spin around. Again, notice this is simply saying our normal vector. So this is the direction that the area vector A will lie in. And as my loop rotates, that's going to line up with B. It's then going to turn away from B. It's going to be perpendicular to B when its orientation is pointing over here. It's going to continue to swing around until it points in the opposite direction of B. So notice that it's phi that's changing in this case. Well, that means B and A, they aren't changing, so I can pull them out. So I've got N times B times A times the absolute value of how that cosine value is changing when I plug in two different angle amounts. I might know how long it takes to go from one angle of orientation to a second angle of orientation. I can plug those two angles in to get the cosine values, subtract them, divide by time, take the absolute value, multiply by NBA. That's going to give me the induced EMF in this case. So we're going to start with our Faraday's law problems by figuring out what's the parameter that's changing in the magnetic flux. Magnetic field, area of the loop being penetrated by the magnetic field, or the relative angle between the magnetic field and the area vector.